Latitude Media, podcast at the frontier of climate technology.
I'm Shail Khan, and this is Catalyst.
I believe with access to mining and downstream capacity in North America, engineers will still really like rare earth magnets, and buyers also will like rare earth magnets because they have multiple options for sourcing of rare earth magnets now. So I'm really optimistic on domestic supply of rare earth magnets.
Well, for all those listeners who've been patiently waiting for a podcast on neodymium, I just want to tell you that I hear you, I see you, and today's your day.
Let's face it, environmental news is often very depressing. That's why we focus on solutions on this podcast. But still, the climate crisis looms large. Rising temperatures, mounting pollution, environmental degradation, they're all warping the planet. And for a lot of species, including us, things don't always look so great. But the story doesn't end there. Every Friday, Living Planet, a show from Deutsche Welle, takes you behind the headlines to figure out what's happening and how we'll get through it. It'll also help you make better choices for a healthy planet and find space to reconnect with the beauty and wonder of the world around us. You can find Living Planet wherever you get your podcasts.
I'm Shail Khan. I invest in revolutionary climate technologies and energy impact partners. Welcome. Well, I've been known to say that the energy transition is, at least to a first order, basically a transition from fossil fuels to metals and minerals. We've talked about some of these winners of this shift here before, battery metals like lithium, nickel, cobalt, as well as other critical minerals like copper. And I'd say there are two common themes amongst those discussions. First, we're going to need a hell of a lot more of each of these things as we go from early adopter of decarbonized technologies to the majority. And second, there's pretty much always a complex geopolitical challenge that we face in that transition, whether it's the Democratic Republic of the Congo for cobalt, or South America for lithium and copper, Indonesia for nickel, and then there's China. Always China. And nowhere are both of these issues actually more prevalent than with rare earth elements. The story there is playing out in real time. Demand is growing, as it is with many of these other elements. Supply is a challenge, and it still largely does come from China, which has just recently, actually, a few months ago, instituted a ban on the export of new technologies for extraction and separation of rare earth elements. The whole area is vitally important and very complex. We at EIP have been on a critical minerals and metals kick for a couple years now, which has resulted in multiple investments to try to solve some of these problems. And one of those investments was Cyclic Materials, whose founder Ahmad is my guest today. We co-led Cyclic's Series A financing last year alongside BMW Ventures. And today, Ahmad and I talked about Cyclic, but also just as importantly, talked about the big picture challenge of securing enough rare earth element supply during the energy transition. Here's Ahmad. Ahmad, welcome.
Thank you for having me.
Excited to have you and to talk about rare earth elements. Starting with the definition, what are rare earth elements? This is actually something that I think probably our listeners appreciate, but I've found a lot of people in the broader public, they hear rare earths and they think of things like lithium and cobalt and other stuff that are not actually rare earth elements. So what are rare earth elements?
So, great question. So, lithium and rare earth elements and some other metals are in a category called critical metals. And that's probably the times that I see people confuse rare earth elements with other elements. Rare earth elements are a group of metals at the bottom of periodic table. And of course, you can graduate high school and not learn about them. These metals are 15 plus 2, so overall 17 elements. And because of their chemical and physical properties, nowadays, we have a lot of applications for them in different sectors, especially back to energy transition. And those are your rare earth elements.
Can you? What are the? I mean, you said there's 17 of them. Are our current uses of rare earth elements pretty evenly spread across the 17 or most of the 17, or are there a few that are dominant where we like really use a lot of whatever neodymium, but not or dysprosium, but not a bunch of the other ones? Like, separate them out from each other a little bit for me.
Absolutely. So out of 17 rare earth elements, there are 5 of them sometimes 6 of them that we call them magnet rare earth elements. Let's take a step back Rare earth elements are used in a variety of applications, in catalysts and glass and different applications alongside magnets. We use them in permanent magnets. And happens that when we use rare earth elements in permanent magnets, which we call them rare earth permanent magnets, those happen to become the most strong magnets that we can make on our planet. So this is really unique to rare earth magnets. From volume side, the 5 or 6 rare earth elements that we use in permanent magnet manufacturing accounts for about 40% of rare earth elements. So 40% of rare earth elements go into magnets. The other 60% does not. But here's the interesting thing. From dollar value perspective, over 95% of rare earth elements are the 5 that we use in permanent magnets. And the combined 60% of rare earth elements carry only less than 5% of the dollar value in the market for rare earth elements. So you can see how valuable permanent magnet rare earth elements are, which are subcategory of rare earth elements.
And which ones are those?
Oh, those are neodymium, praseodymium, dysprosium, terbium, and samarium. And nowadays, we mix a little bit cerium into magnets as well. Now, neodymium and praseodymium are among the light rare earth elements, and those are basically the very important ingredients of permanent magnets. Dysprosium and terbium, we use them in tiny little bit concentrations in magnets to give them really high temperature, good quality magnets that we use in electric vehicles and some other applications.
And this is one thing I've always wondered, right? So we're going to talk a little bit later about, do we really need the rare earth elements? Can we displace them with something else? We'll focus probably on this permanent magnet thing, because that's the most relevant to the energy transition. As you said, it's where the vast majority of the dollar value is. Why is it that this basket of rare earth elements makes permanent magnets so much stronger? Like, what is it about them that enables that?
Oh, it's their physical and chemical properties. So it happens that when you combine neodymium, praseodymium with iron and boron, with very specific physical properties that they have and they carry, you end up with really strong magnets that has significant energy density in a small volume. And that is the differentiator of these type of magnets, rare earth magnets versus other magnets in the market. And we count on this property of rare earth permanent magnets significantly in the energy transition. Simply put, those permanent magnets, now from the application side, one of the areas that we use them very often is when we want to convert electrical energy into mechanical energy, from a battery to driving a car, or the other way around, from mechanical energy to electrical energy in a wind turbine generator. So when we use rare earth permanent magnets, we happen to make the most efficient electric motors or generators out there that we know of. And if you're putting a lot of dollars into a battery pack in an EV, it just makes sense to tie it up to a very efficient electric motor and consume that electricity efficiently. And when you think of systems, then using permanent magnet electric motors becomes really important.
Yeah, so that speaks to why not only do we use a fair amount of rare earth elements already today, but the expected trajectory follows the expected trajectory of the energy transition, primarily in things like electric vehicle adoption, to some extent wind turbine development as well. So now we're back in the category with some of the other energy transition metals, as you said, like lithium, cobalt, nickel, and so on, where there's this secular growth trend in demand. We'll come back to demand. I want to talk about supply. So let's start with where we get rare earths from. When there's virgin mining today, where are the rare earths in the world? And then walk me through the supply chain as it exists today.
Sure, absolutely. So 2 things. If it doesn't grow, you mine it. So we start with mining. And the second thing, rare earth elements are recycled less than 1% globally. Those are among the least circular metals that we know of out there. So basically, the primary source of rare earth elements today is mining of rare earth elements. About 60% of that happens in China, and the other 40%, give or take, is happening outside in other countries, including the US. Now, that 60% in China, some of that is byproduct of iron oxide mining as well. But overall, majority of mining happening in China. It happens that in the downstream processing, though, majority of those mined materials outside China are shipped to China. So China acts really like a vacuum here, brings in all the material to China and processes and produces magnets. The processing is over 90% done in China, and magnet manufacturing over 95% done in China. And from there, it's shipped around in final products in electric motors and other units for consumption all over the world.
And I think, it's true in a number of these categories in critical minerals and metals that China has found itself in a pretty dominant position with regard to processing and refining. So it's especially dominant in rare earth elements and in permanent magnets. But, that is true in lots of different categories. What is interesting, though, is that China is also the home to the majority of the mining in rare earths, which is not true of all these other categories. You look at something like lithium, right? The mining takes place in South America or in Australia, and then a lot of the refining takes place in China. So is the reason that China is dominant on the mining side because the resource happens to be in China? Or is it just that China put more effort and investment into building a rare earth mining industry, or as you said, a byproduct of iron mining than other countries have?
Oh, the combination of both. So in Canada and US in 1960s and 70s, US and Canada used to be a leader in production of rare earth elements. Significant production of rare earth elements from mining side was done in other countries as well, outside China. Mining of rare earth elements comes with some unique challenges. For instance, radioactivity of ores that come off the mines usually is one of the challenges. That radioactive materials are, from concentration perspective, high enough that they cause really environmental problem on that side, but low enough that they can't be economically recovered from the material. So things like that over the time basically put pressure on mining of those metals outside China, in North America specifically, and those eventually ended up in China. So China gradually picked up on production and mining of those metals, as well as the other environmental impacts. After mining, when you have the ore or concentrate that comes off a mine, usually the chemical process that you would require to put the material through to get to the metals at the back end is pretty environmentally I'm going to say challenging process. And when you have that in North America, it's basically not ideal. So we ship those processing capacity in the past 20, 30 years to China. And all of a sudden we woke up and they had all the production capacity within Chinese borders. And that happened mostly for rare earth elements from mining all the way to downstream. But as you said, for some other metals, they really heavily invested in downstream processing of copper, downstream processing of other metals like cobalt, like graphite, like lithium. And that basically all of a sudden gave them a lot of advantages over production of downstream products. Whereas in US, we don't have much of those metals available today to build the plants. This is interesting to note also that rare earth elements on themselves are about, in 2024, $20 billion market. But the downstream or the industry they unlock is in trillions of dollars. And I think at some point we did a miscalculation on the priority of how important these metals are in North America. And to be frank, China has been publishing their 5-year plans every 5 years in the past 20, 25 years. And they constantly said, we want these metals in China. And here we are. They have it in China.
So we'll come back in a few minutes, I think, to what are the solutions to this geopolitical challenge that we face. But first, just can you walk through the steps from raw ore mining to a magnet that goes into a motor that goes into a vehicle? What are the steps along that process?
So it starts with mining. So you produce, you mine the ore. Again, majority of that happens in China. To some extent, that happens in California as well by MP Materials. The next step is to take the ore, which has only 1 or 2% rare earth element in it, sometimes even less than that, to a product that is called concentrate. Now, concentrate usually has 50-60% rare earth oxide value in it. And that also is quite a bit produced in China and a little bit outside China as well. Now, majority of concentrates now are being shipped to China. When it comes to processing now, give or take 90% of concentrates are processed in China. In this process, basically, you take the concentrate and with very heavy chemical process, drive it all the way to now called mixed rare earth oxide, which is a basket of rare earth elements that comes off as a final product from the concentrate. Now, mixed rare earth oxide really depends, the quality of mixed rare earth oxide in each plant or each deposit will depend on the ore that they processed. For instance, for the material from California that is shipped to China, usually you end up with about 70 to 80% of lanthanum and cerium oxide. Those are the metals that don't carry much value. And this number will be different in other mixed rare earth oxides that come off other deposits, but universally 70, 80, 85% of rare earth oxides are going to be negative value rare earth oxides in those mixed rare earth oxide baskets. For cyclic materials, for us, it's different because we recycle only magnet metals, and I'm going to come back to that.
That's a key point, though, and it's part of why I wanted to ask at the beginning about separating out the different rare earth elements from each other, because you could think of them as one basket. But actually, what's interesting about the process as it exists today, as you just described, is that you mine an ore, you concentrate the ore, then you process it, you get this basket of things. So whereas with, lithium, lithium is lithium, but in rare earth elements, what you're getting is a basket of rare earth elements, even after you've gone through your processing step. And as you just said, the majority of what is inside that basket is actually negative value. What you really want is the minority of what's inside that basket you've already processed, which is mostly just those 5 to 7 rare earth elements that we actually care about.
Absolutely. And then, again, those mixed rare earth oxide now have to go through the process of refining. And that's basically a long chain of solvent extraction unit operations, usually done in 1,000 or so steps, sometimes even more, to separate rare earth elements, each of those into an individual basket. Now, you have pure cerium oxide, you have pure neodymium oxide, you have pure dysprosium oxide. Some of those are mixed together, for instance, NdPr and whatnot. Now, solvent extraction has been around for many, many years. The reason solvent extraction or refining for rare earth elements is really complicated is because the chemistry of each individual rare earth elements out of the 17 is pretty similar to one another. So you're now separating metals that they behave pretty similar in the process with one another. That's why the efficiency of process is really low, so long chain of solvent extraction happens to do so. This is pretty expensive process as well, and produces a lot of waste simply because, let's just state it again, around 80% of your rare earth elements in mining industry are value negative rare earth elements that we way overproduce those, so hence they are value negative. Now, after you produce individual rare earth oxides with high quality, then the next step is to metallize those. So you make metal out of those oxides. You basically remove the oxygen and you make metals. In this step, basically 95% of the process is being done only in China. We don't have much metallization industry outside China simply because the oxides are not available outside China. And the next step is basically magnet companies will take those alloys of magnet after metallization and they grind or cut out the magnet pieces that they need in the size and shape that they need, and then they insert it into the electric motors, and then you have your electric motor for electric vehicles or other applications. And that's basically as close as to a product you get. So then the next step is to ship that product into the market.
Okay, so that's the process that exists today. Before we talk about what to do about it, actually, I want to go back to the geopolitics for 1 second, because as we've said multiple times, China is pretty dominant here. Trade tensions between China and the Western world have been high of late, and that has trickled down into rare earth world. So what's the latest on China export curbs in rare earths, and what are we to make of it?
So one thing that we really were expecting to happen a few years ago happened last December. China put a pause on exporting of any technology related to rare earth elements, mining and recycling and processing. So that's really important to understand, simply because they are trying to maintain their dominance in this space and not give it away. At the same time, to counterbalance that, we have IRA and other vehicles in North America, Europe, and other jurisdictions to help industries to grow in those countries. For instance, Department of Defense awarded Linus in Texas with over $200 million to build capacity on refining of mixed rare earth oxides, or Department of Defense awarded over $100 million to Vacuum Schmitz, a magnet manufacturing company, to build their facility in South Carolina, which we have partnered with them. So there's a lot of efforts in this space happening to reduce the dominance and dependence of rare earth element supply chain with China, and I'm really optimistic on this side, because those efforts I really think this time around are being done really nicely and the right way they should be done. But still, in 2024, we are heavily dependent on China on sourcing of those materials.
Okay, so let's talk about what to do about it. And I think of it as being 3 categories of things that you can do about it. We're going to save the one that you do, which is recycling, for last. But the 3 categories in my mind are: first, we could change the demand picture. Now, I don't think that's going to be changing the demand picture by reducing demand for electric vehicles. I think it would have to be, magnets, permanent magnets that do not require rare earth elements, or that require less of them. So that's one category. Second category would be just ramp up our supply of virgin mining and processing outside of China in the Western world in various places. As you said, there's some of that already, particularly on the mining side in California. You just do a lot more of that. And then the third is recycling, which we'll save for the end, because that's where you're focused. But let's talk about those first 2 first. What have you seen out there in terms of developments to try to make rare earth elements less necessary if we are building permanent magnets?
Sure. So let's start with rare earth-free magnets, because there is a conversation going on that, and some companies are looking into design of rare earth-free magnets. Just to be clear, rare earth-free magnets do exist today. So Al-Nickel group of magnets and ferrite group of magnets are already out there. The industry wants to create newer category of rare earth-free magnets that possibly they could use in substitution to rare earth permanent magnets in electric vehicles, wind turbines, and other applications. I don't believe we are there yet, but out of necessity, I believe this is the right step to take. And some of those magnets already are being produced by some companies out there in the US as well. And appears that some of those magnets eventually will be consumed in speakers industry and other similar industries. Again, the majority of drive of rare earth element consumption, especially on the magnet side, are going to come from wind turbines, from electric vehicles, and some other applications that speakers are a small portion of that. So we still will have the demand for rare earth permanent magnets out there in the next years to come. I haven't seen a solution to that just yet.
And is that because, as you said at the beginning, the reason rare earth elements are so valuable in a magnet is they make the magnet stronger? And so is it true that the applications where these rare earth free permanent magnets make the most sense are the applications where the requirement for magnet strength is lower? And that's what's true about speakers, for example, but not as true about wind turbines and electric vehicle motors?
Correct. So how strong the magnets are per unit of volume. So that's one indication for quality of the magnet. And the second one is at high temperature, they still remain magnetic. So they don't lose their magnetic properties at elevated temperatures. And now when you have a speaker, usually is at room temperature, maybe a little bit elevated temperature. But when you have a traction motor of an electric vehicle, because of the rotation, you usually have heat in there. So that's a little bit different game in there. So those qualities and the energy density in the magnet basically are the reasons that some of those magnets haven't found use in high-end applications in industry just yet.
Okay, so, all right, so substitution may play a role eventually, kind of hard to tell. Technology is not quite there yet, but you could imagine that. So second option is just ramping up supply ex-China. What do you see happening there? And that's supply both from a mining perspective and then obviously equally importantly from a processing and refining perspective.
This is where I'm quite a bit optimistic. So, for instance, mining industry in U.S. and other jurisdictions are looking into extraction and processing of rare earth elements. For instance, MP Materials in past few years have shown that they can basically mine and ship the material to China and process it in China. So there is already one step of the process completed in the U.S. Now they're looking into downstream to bring the processing back to U.S. and process the material up until production of magnet through MP Materials. So they have been having some press releases on that side in the past few months and making advancements on production of magnet and also production of high quality neodymium, praseodymium in US on that side as well. I think mining and processing is the area that we have spent a lot of money in North America and Europe, of course, on it as well, and eventually will come very handy. Simply put, on the mining side, we have resources out there that are producing concentrate today, so that's good. On refining side, for instance, Linus, that already is refining in Malaysia, is building a plant in Texas. So that's another really strong indication that very, very likely we will have refining capacity in the US as well. And on magnet manufacturing side, also companies like Vacuum Schmitz, which have years of experience in manufacturing high quality magnets, are starting to build capacity in North America as well. So from that perspective, I'm really optimistic. Now, today, when it comes to consumption of magnet in the companies, let's say OEMs, car manufacturers, there are two stakeholders in there. Engineers, they love rare earth magnets. They can't get enough rare earth magnets, actually. The second stakeholders are buyers and OEMs, and they dislike rare earth magnets because their supply chain is heavily associated with one country. Now, fast forward a few years, I believe with access to mining and downstream capacity in North America, engineers will still really like rare earth magnets, and buyers also will like rare earth magnets because they have multiple options for sourcing of rare earth magnets now. So I'm really optimistic on domestic supply of rare earth magnets.
Okay, and that brings us to category 3, the category that Cyclic is focused on, which is recycling. You said before that we only recycle 1% of rare earths today, which, anybody who knows something about lots of other commodity metal industries like copper and steel and so on, we recycle a fair amount of all those things. Why is it that we don't recycle rare earths today? And then obviously that will dovetail into what are you doing about it?
Absolutely. Yes, true. Rare earth elements, which actually, when Department of Energy looks into critical metals, categorizes them as the most critical metals in the category of how critical those are. Happens to be the least circular metals as well. So we don't recycle much of those at all today. Simply because when we recycle end-of-life products, magnets being magnetic attach to steel and travel with steel into steel recycling plants, iron recycling plants. And because of the chemistry in the steel recycling plants, rare earth elements report to a phase or chemistry and steel production plant that is called slag. It's a glass, just looks like glass on our windows, really, and rare earth elements are locked inside the glass for good, forever, and thermodynamically really stable, and you can spend a lot of money recycle those and recover those, but that would not make you money and would be very environmentally pollutive as well. So that's the main reason why we don't recycle rare earth elements today, because we lose them into steel recycling plants.
Right. It's the process of steel recycling that locks the rare earths away permanently because they end up in the steel slag and, as you said, extremely thermodynamically stable. So you theoretically could get the rare earths out of there, but it would come at such an energy penalty, it would never be worth it.
Correct. It would be very expensive and environmentally harmful.
Right. Okay. So how do we solve that?
So we do have two sets of technologies in our company. The first technology basically in our spoke operations separates magnet from everything else. So imagine a traction motor of an electric vehicle comes in. We separate copper, aluminum, steel, and magnet into 4 different buckets. Now, copper, steel, aluminum, they already are known in the market how to treat those, so we sell those off. Magnet, we hold on to it, we send it to a secondary operation or technology that we have in the company, which is the core. The technology is the core of our hub operation now. So we have a spoke and hub model. In our hub, magnets would come in, and with hydrometallurgy process, we would basically process those magnets, and we produce mixed earth oxide. Now, I will point out that our mixed earth oxide is one of the highest quality mixed earth oxide today available in the market, actually, simply because it's purely concentrated with magnet rare earth metals.
Right. The other way to put that is that if you're mining an ore, you're getting a bunch of rare earths out with no regard from the ore body as to whether those are the ones that we humans happen to care about or not. Whereas if you're recycling, you are starting with only the stuff that we used in the first place.
100%. But above that, when you mine rare earth elements, very, very often, in majority of cases, you have some radioactive materials to treat as well. But in recycling, because we recycle end-of-life products that already have been refined, we have no radioactivity in our operations because nothing comes as a feed to our processing plants.
Okay, so Cyclic's process, as you said, is 2 steps. Step 1, you remove the magnet from the steel, and obviously from the other things as well, which you can sell off as commodity metals like copper. Step 2, you take that magnet, you send it to a central processing facility. That processing facility gets you your basket of rare earths, mixed rare earth oxides, out of the magnet. I guess the question is, why 2 steps? You're doing this hub and spoke model. Why is that the right way to run this kind of recycling operation?
Great question. So we do recycle end-of-life products that carry magnet. And end-of-life products consumed by human have really large entropy, meaning that they are distributed on our planet. Wherever we have more population, we will have more of those end-of-life products. In recycling business, one of your key elements to optimize for is your logistics and shipping and handling costs. So we would like to be closer to our feedstock sources. From that perspective, having a few, for instance, in North America, spokes will make sense. So we would be closer to the centers where those end-of-life products are available. We will process those. And simply put, iron Aluminum and copper have large market with distributed market all over the planet, so you can tap into that market. But magnets, which are less than 5% of feed that comes to a spoke, could be shipped to a central plant, and you could, for whole North America, you could have one central plant, one hub, and process the magnets in there and produce the rare earth oxide in there. So that would give you the optimum operating costs on the spoke side and bringing in feedstock, and also optimum capital costs on the chemical plant, having just one central location to do so.
So one of the questions that gets asked a lot in the context of battery recycling is like, what portion of global demand could recycling actually supply? Like at what point, in battery recycling, people say if we recycle all the batteries that are available to us and in some future state, we don't need to mine so much virgin lithium, nickel, cobalt, graphite, et cetera. What is that in the context of rare earths? Like what portion of global rare earth element demand do you think could be met by recycling, and when?
So when it comes to other metals like copper, aluminum, steel, we recycle, give or take, 40 to 50% of those metals. Even for metals that we produce a little bit of those, like germanium and others, we recycle about 50% of those metals as well. When it comes to rare earth elements, we are doing really a poor job these days at around 1% recycling. And I believe rare earth elements also could be recycled at around 40, 45%, 50%. So there is a significant market possibility opportunity out there for rare earth recycling. Cyclic Materials plan is by 2030, 31, 32, we will be recycling around 2% of the world rare earth elements. So, and also our vision is that rare earth elements recycling is not a substitute to mining. It's just to reduce the pressure on mining. And also when you recycle rare earth elements from an environmental standpoint, you produce far less carbon dioxide. You consume a fraction of the water that mining industry consumes to produce the same amount of product. So from those instances also, we really need more and more of rare earth recycling, but because of the increase in consumption of the metals in the industry, we can't really just rely on recycling, and we will need a combination of healthy recycling and strong mining operations as well.
All right, Ahmad, this was enlightening. Thank you for your time. We obviously wish you the best and wish the industry the best at figuring out how to develop a geopolitically secure and clean rare earth supply chain.
Thank you so much.
Ahmad Ghahraman is the CEO and co-founder of Cyclic Materials. This show is a production of Latitude Media. You can head over to latitudemedia.com for links to today's topics. Latitude is supported by Prelude Ventures. Prelude backs visionaries accelerating climate innovation that will reshape the global economy for the betterment of people and planet. Learn more at preludeventures.com. This episode was produced by Daniel Waldorf. Mixing by Roy Campanella and Sean Marquand. Theme song by Sean Marquand. I'm Shail Khan, and this is Catalyst.